let me introduce Amiel Paz.
Okay.
Paz, sorry. He's also from Glover, NYU, Shanghai. Then go ahead.
Thank you. And I'd like to thank the Quantum Multiscale organizers for giving me the opportunity to talk about this work. I'm going to talk about our group's recent methodological development work meant to address particular challenges in the QMMM dynamics in the condensed phase and the simulation in particular of a set of systems that possess what are known as solvent-supported states. And I'm going to talk about the associated challenges of simulating dynamics with solvent-supported states with QMMM. I'm going to be talking about two of our recent methodological developments, the flexible boundary layer with exchange, QMMM boundary potential, and the use of ECPs on atoms to address the problem of electron spillout during dynamics. I'm also going to talk about the application of these methodologies to simulations of a challenging prototypical system, solvent-supported states known as the hydrated electron. And so to give a bit of background about our interest in solvent-supported states, first let me talk about what these solvent-supported states are. These are states that are either weakly bound or unbound in the gas phase, and then become more stably bound in the presence of a solvent environment. And so these solvent-supported states involve a very diffuse electronic states having a very intimate coupling with its local solvent environment. And so attempts to treat this strong solute-solvent interaction would mean that you need to be able to include some of your solvent environment within your QM region. And therein lies a new set of challenges that we don't often encounter in other QMMM systems wherein we can treat the chromophore quantum mechanically and the rest of the solvent environment with molecular mechanic force fields. And so the dynamics of these types of systems are interesting because these systems have been more recently implicated in mechanisms for biological photodamage. And in particular, this species, which is known as the hydrated electron, has been implicated in dissociative electron transfer to DNA. So a bit more about this species. This hydrated electron is an excess electron in a liquid water environment, and it occupies a cavity in liquid water. It's very commonly generated through radiolysis. Historically, it's also been a very interesting system for exercising mixed quantum classical simulation methods. And so this system is going to, of course, present challenges for simulation in QMMM, and I'm going to talk about those challenges in a moment. But let me talk about the traditional starting point for attempting to do QMMM dynamics for a system like this. And so we are going to start, of course, with our system. We have solvated 76 QM waters, and these 76 QM waters support or solvate the hydrated electrons wave functions. The remaining solvent cap in this system that we have here is treated with molecular mechanics force fields. And we are using diffuse basis functions. And the reason for this is that the hydrated electron centroid is a few angstroms away from any one of these solvent molecules because of the fact that it resides in a cavity. And so because of its rather distal proximity to the other solvents in its local environment, we need to be able to, we need to use diffuse functions to be able to treat the hydrated electrons wave functions. And we are including dynamic correlation through density functional theory, and we're using the PBE hybrid functional with 57% of exact exchange, as we found that that yielded pretty good transition energies in agreement with known experiment. And so this is our starting point. We want to be able to simulate the dynamics. And here I've zoomed in into what our QM region looks like. You can see the amount of interaction with the local solvent environment. You can see the hydrated electron has some overlap with the local water molecules, and so this starts to suggest the importance of being able to include solvent in your QM region. And so having laid out our starting point, I'm now going to talk about two challenges that we came across and our solutions to those challenges in our attempts to simulate the dynamics of the hydrated electron. The first is the ability to maintain QMMM separation for a liquid simulation. And this problem is particularly exacerbated by the fact that we have now solvent treated at both QM and MM level of theories. And so in order to be able to resolve ensemble average properties and also to be able to get reasonable snapshots for excited state dynamics, reasonable snapshots for the initial event of photoexcitation, we need to be able to equilibrate the system. And to equilibrate the system, we need to get long ground state trajectories. And if we try to run long ground state trajectories in this traditional QMMM formalism that we have here, the QM and MM atoms will eventually diffuse across the partition. And that is because we have liquid in both of our QMMM regions. And of course, those liquid particles have a tendency to diffuse over long enough timescales. And so this is not an unknown problem. You can see how particularly severe this problem with just a simple Q diffusion, then you can see that the QM waters will diffuse into the MM solvent environment rather quickly over the course of dynamics. And so, as I mentioned, this is not an unknown problem. There have been several strategies that have actually been developed, and I'm going to talk about these two strategies. These two strategies can be thought of in terms of their relation to the density of the QM region. So the adaptive QMMM set of approaches allows fluctuations in the number of QM atoms over the course of dynamics while keeping the volume of your QM region constant. So the advantage to this set of approaches is that it allows for this diffusion because it allows the changing identity of your QM and MM partitioning. That is, the number of atoms that you define as QM and the number of atoms you define as MM can change dynamically as a function of time. And is straightforwardly applicable to heterogeneous systems wherein you have a mixed solvent environment. But one of the problems is that, of course, you have this QM number of QM's atoms fluctuating. You're going to introduce discontinuities at the QM-MM boundary due to the sudden changes in your potential from changing the identity of your atoms from QM and MM. And so to actually combat this problem of sudden discontinuities, you would need a large enough buffer region so as not to affect the dynamics of the systems that you're interested in, which is usually just within the core region of your large QM region of your QMMM partitioning. The other set of approaches is based on what's known as constrained QMMM. That is, we keep the number of QM solvent fixed, but we allow the volume of our QM region to fluctuate. So we keep a constant number of QM particles. And because we don't allow this change in identity, this becomes less prone to the same boundary artifacts that adaptive QMMM is prone to. If we're particularly careful about how we construct our constraints, then we show that we can actually reproduce the correct ensemble averages in the absence of constraints. But the difficulty with this is that it's so far only been applied to homogeneous systems, that is, only with systems that have a description of a single type of solvent molecule. And certainly the presence of a boundary potential where we constrain the QM atoms to stay within the QM region and the MM atoms to stay outside of the QM region will influence the dynamics. And so the key question is, on what timescales are we concerned about how those will influence the dynamics? And so our development follows in the latter set of approaches of constrained QMMM. So we developed what's known as the flexible boundary layer with exchange. This is, again, a constrained QMMM approach. So the boundary potential preserves the partitioning of the QMMM atoms through this repulsive wall, and allows the QM volume to flexibly change. It's important that we have constructed this potential in such a way that ensemble averages are rigorously preserved. And because the potential acts only on a very narrow layer of the boundary, of the QMMM boundary, the inner region dynamics are preserved. And so here I have a schematic of how we've modified the QMM Hamiltonian so far. We have our traditional electrostatic and possibly polarizable embedding terms. We have our mechanical embedding terms, which show up as the non-bonded Lennard-Jones interactions between your QM and MM atoms. And we've now added this new term. It is a classical QMMM boundary potential that acts in a pairwise manner between QM and MM atoms in order to prevent this inner boundary diffusion. And so how does the theory of flexible work? The idea is that we have a bath of like particles. For example, in this case, we have a bath of all water molecules. And let's say we were to color these molecules in some particular way, right? We choose to color some of these water molecules red, some of these molecules blue. Well, the idea is that if all of these atoms or all these particles or all these molecules undergo the same potential, then no matter how I color these molecules, they will all contribute the same Boltzmann factor, right? This exponential negative beta times the value of the potential at a particular part of configuration space. So what's interesting about that is, of course, knowing that the Boltzmann factor is going to be invariant to exchanges, I can actually introduce a reweighting in anticipation of the fact that I know that allowing QM and MM mixing, because they do not contribute the same potential, will introduce artifacts in the dynamics. And so what I can do is I can choose a reweighting, and this reweighting works in such a way that I achieve the same ensemble averages while having larger weights for a particular set of configurations. As an example, those that have the QM region nicely localized in its QM partition and the MM region away from the QM partition, and give a vanishingly small weight to those configurations that allow mixing. And so this so far, right, I'm talking about this in terms of weights. How does this translate to what we do for dynamics? Well, it turns out that this reweighting can be reformulated in terms of a boundary potential. You just take KBT times the log of that particular reweighting term, and what we get is a novel boundary potential. And this boundary potential can actually be applied to reinforce this reweighting over the course of the dynamics, and thus allow QM and MM separation to be maintained. And so we can see with this potential what the effect on the QMMM boundary is now. We see that once we have this potential turned on, the MM atoms stay outside of the area of the QM, and the QM stay within the area and the area of the QM region and do not diffuse across that partition. Now I'm going to allude to the second problem. Having addressed the problem of maintaining QMMM separation, we now talk about a particular challenge in general with QMMM and diffuse electronic states that you're going to run across, and that is the problem of preventing electron spillout. So to introduce the origin of the problem of electron spillout, it really requires us to talk about Pauli repulsion. And a nice example of Pauli repulsion is the problem of Rydberg and valence type mixing in the LUMO of ethylene. So if we were to run a calculation for ethylene, what we should see is that the lowest excited state should be a pi star state. But in environments where we have a lack of Pauli repulsion, that is a lack of the orthogonality constraint of the electronic environment to the electronic environment of the MM atoms to the electrons on your QM atoms, then what we see is a severe artifact known as Rydberg valence mixing. And so what we achieve, especially if this Rydberg type state is allowed to have a large amount of overlap with the positive point charges in your MM environment, is a stabilization, an artifactual stabilization of the Rydberg type state that brings it lower and lower in energy, and that actually results in the mixing with what should be the pi star type orbital for ethylene that we see here. How does this manifest in particular for the hydrated electron? Well, because the hydrated electron we've chosen to represent with these very diffuse basis sets. These diffuse basis sets have extensive overlap with positive point charges in our solvent environment. And those positive point charges drive the diffuse electronic state of the hydrated electrons, the diffuse electronic wave function of the hydrated electron to the boundary over the course of the dynamics. And what you get is your hydrated electron starts to become localized at the QMMM boundary after some point of dynamics. And so we want to have a systematic way to prevent that, but we also want to do it in such a way that we can afford the expense of having an account of Pauli repulsion without turning MM back into a QM. And this is practically achieved through what are known as effective core potentials. So these effective core potentials were designed to model the effect of Pauli repulsion originally of core electrons treated implicitly to your valence electrons in the system. This is the original intent of effective core potentials back when they were first developed. But we showed that this practical idea of mimicking Pauli repulsion can also be applied to preventing electron spillout by placing them on atoms. And this has already been demonstrated now by a few authors. Now, it's of course going to be obvious that placing ECPs on all of your atoms actually incurs a rather steep computational expense because each of those involves an ECP integral calculation. It should also be obvious that you don't need to put ECPs on all of your sites because these ECP integrals die off very quickly as a function of their distance to the QM region. And so we developed a way to actually pre-screen sites that contribute to the total ECP energy negligibly through a modified bound developed by Sean Hill a few years ago. So this takes advantage of the decaying strength of the ECP integral as those sites get further and further from the QM region. And so when we, so this becomes a practical tool for dynamics because we're only ever putting ECPs on those atoms that have a non-negligible contribution to the effect of applying Pauli repulsion to our QM densities. Now, another problem comes with the fact that when I now write our new QMMM Hamiltonian, again, reintroduce electrostatic and mechanical embedding, the boundary potential that came from flexible, and we have a new term that comes from the ECPs. This is the Pauli repulsion that comes from the environment. But wait, that Pauli repulsion is actually already supposed to be taken into account by the Leonard-Jones short range terms. And so there actually becomes an overcount of Pauli repulsion that is included with most force fields that people use out of the box for QMMM dynamics. And so this necessitates a scaling for repulsion. And I point out that Darren York has actually emphasized that this should be done for QMM environments, even without the presence of these effective core potentials on atoms. You really should rescale your short-range Leonard-Jones interactions to be more appropriate for capturing Pauli repulsion between QM and atoms. And so we've done this in such a way that for water, for example, we've done this in such a way that we've been able to reduce the water interaction at a full level of theory. And so we apply this rescaling to our simulations of the hydrated electron. But now we demonstrate that when we put ECPs on the waters, we do actually recover the correct pi star character of ethylene's LUMO. So then we are able to treat properly in the condensed phase the lowest excited state, which should be a pi star transition in ethylene. And furthermore, you can see the effect of ECPs based on these results from ground state dynamics of the hydrated electron. So the QMM boundary for a system with 32 QMs is around the 6 angstrom mark relative to the distance of the hydrated electron centroid, plus its radius of gyration. And over 10 independent trajectories, we see that those ECPs keep the hydrated electron nicely localized in the QM region. So we have confidence in our technology, in the ECP technology, in preventing electron spillout over the course of dynamics. And so this is the key result of of our methodological developments, this modified QMMM Hamiltonian that includes traditional Coulomb and mechanical, traditional electrostatic and mechanical embedding with a rescaled short range part, a classical boundary potential between QM and MM atoms, and a new operator on the electronic degrees of freedom that is meant to mimic Pauli repulsion from the MM environment. Now I'd like to show some results for dynamics of the hydrated electron. So for flexible, you can see that we are actually able to reproduce results that were previously published for the hydrated electron on the radial distribution function. To briefly go into what the radial distribution function is, this is meant to give a metric for how the density varies as a function of some distance relative to the density of the particle in the bulk. So of course, in asymptotic distances, the densities should be equivalent to the bulk density, but at short range with respect to a particular distance, there should be a particular structuring. And the structuring introduces the idea of where the solvent shells for a particular species is. For example, we know roughly where the solvent shells of the hydrated electron are based on the hydrated electron oxygen RDF and the hydrated electron hydrogen RDF. And we see that we're able to reproduce very well the peaks that were previously computed by John Herbert's group. We also see that we are able to demonstrate some new insight that's not actually seen in previous one electron pseudopotential models, wherein the only quantum degree of freedom treated explicitly is the hydrated electron, and every other many electron interaction is analytically fit. So we see that when we have an explicit account of many electron interactions, there's a redshifting in the OH stretch in the Fourier transform of the band gap correlation function for the hydrated electron. And this OH stretch speaks to an overlap of the hydrated electron's cavity type S-like orbital with the antibonding orbitals of the nearby water environment, weakening the OH stretch for those particular antibonding orbitals that it has overlapped with. Now I'd actually like to go into some results for the excited state dynamics. And what we again see is actually something that is at variance with the one electron mixed quantum classical model. We see that for these a set of surface hopping trajectories that we predict a relaxation on the excited state of the hydrated electron following photoexcitation, while the mixed quantum classical model actually predicts a destabilization on the excited state of the hydrated electron. And this is this destabilization is not corroborated by recent TREPS results from Toshinori Suzuki. In fact, there should be a stabilization of the hydrated electron's excited state binding energy as a function of time immediately after the photoexcitation, which is something that's actually captured by our QMMM results. And here we take the lifetimes that come from those surface hopping trajectories, and we fit it to an exponential decay. And what we see is that this lifetimes actually fit nicely with a time decay that is on the order of less than 100 femtoseconds, which is something that has been historically challenging for predicted excited state lifetimes with one electron pseudopotentials. Finally, I'd just like to show a movie of what these, a representative movie of what these surface hopping trajectories look like. So what you see is the P lobes fluctuating and breathing as a function of time, corresponding to the localization of the hydrated electron's wave function, either mostly on the left or the right lobe, before finally collapsing onto one of the lobes and then slowly equilibrating back on the ground state. And so the insight from these dynamics is, of course, something that probably wouldn't have been possible without the technologies that we developed for QMM simulation of condensed phase systems. And so with that, I'd like to conclude by, again, emphasizing the development of our technologies flexible for the treatment of liquids at a QM level of theory with MM solvent, important for eventually simulating proton transfer reactions, water splitting reactions, et cetera. And ECPs fixing the problems, ECPs fixing the problems of spill out from molecular excited states and solvent supported states. We also use these technologies to simulate the hydrated electron's dynamics and find lifetimes in better agreement with experiment compared to previous one electron theories. I'd like to end on these open questions. How do we combine MMECPs and mechanical embedding generally, not just for water? So how do we do this rescaling of Lennard-Jones parameters in a more automated fashion for systems with different, with more than just water? And how do we extend flexible to heterogeneous systems wherein we have more than just the water, more than just a single type of solvent molecule in our environment. So this is going to include liquid mixtures as well as electrolytes in our solvent environment. With that, I'll take any questions. How long was that actually, if I might ask? If I have time to field questions.
It's fine. You have time for a few questions. We are going to move
Great.
like 5 minutes. And
oh, great. Okay.
Then thank you so much for your great talk. I really enjoyed it too much. Then the floor now is open for questions. We have like few questions, small, short questions. Then please unmute yourself.
I have a question.
Sure, John.
Yeah, thanks. That was really nice, and I've read some of these papers, but maybe not the excited state stuff. So, what does this say about the adiabatic versus non-adiabatic relaxation mechanism? Do you capture that?
Oh, so I would say that we do capture it, particularly because we are capturing the lifetimes. Are you talking about the particular microscopic origin of the decay, John? Certainly
no,
the lifetimes.
Just the idea that I mean, this was controversial for a while until the time-resolved photoelectron spectroscopy sort of resolved that the short time, the very short time scale is on the excited state. So it's very short internal conversion followed by much slower ground state relaxation.
And we demonstrate that it is exactly that.
It's okay. So okay. So it just went by too quickly. So it's 30 femtoseconds is your excited state lifetime. Is that
no? 70 femtoseconds is following this
okay.
This delay period where we see no appreciable decay. We see we begin to see decay in the populations from our surface hopping trajectories, but when we fit to an exponential curve, what we get is a sub 100 femtosecond lifetime, and that is something that is strictly that would strictly support the non-adiabatic mechanism for the excited state decay. And briefly speaking, it's sort of alluded to here. What you see is an ultra fast separation of the lobes. And those lobes begin to shuttle the charge density between the excited state before it gets to the point where those p lobes split so far apart that the coupling between them becomes negligible. Then the coupling, of course, modulates the energy gap, and the energy gap becomes small. And then what you get is essentially a collapse of that charge density onto one of the lobes. So that's the picture that we have surmised from our dynamics so far.
Okay, thanks.
Okay.
I have other questions, but I don't want to monopolize the discussion.
We have breakout.
I'll let someone else.
We have breakout.
Then I think we have just the right time to start with our next talk.
Okay.
Thank you so much, Amiel, again. Then
all right, thank you.